Welcome everybody to the second webinar for the Hercules Dome Ice Core project. It's great to have you here. If you were here last week, this is going to be identical, so you may want to leave. However, the questions and discussion at the end may be different, so you should certainly feel very welcome to stay. So this is, as we advertised it, an informational webinar to tell folks about this significant NSF-funded community research project. And it's being hosted today by myself, Eric Steig, and my colleague TJ Fudge, both at the University of Washington, along with a number of collaborators, institutions listed on the bottom there. I want to start by highlighting a few key people. So this is the leadership team, in addition to me and TJ, for the Ice Core planning. Murat, Joe, Heidi, and Mark at the institutions as shown. And I also want to give a shout out to Knut Christensen and Nick Holschuh and the multiple University of Washington graduate students who have been involved with and leading the site selection work in the field at Hercules Dome. And also some of the results that I'll show just in one slide today come from some climate modeling work that I've been doing with a large list of people at British Antarctic Survey, University of Vienna, and UW listed at the bottom there. A bit more about key people. Getting a large ice coring project like this together takes a lot of work and planning, and we're extremely reliant both for planning and ultimately for drilling on the folks that run the US ice drilling program, of which there are many, but some key people are shown here. Mary Albert at Dartmouth, Chrissy Sloney, and Jay Johnson, lead drilling folks at the University of Wisconsin. Matthew Kippenhahn and a team from the Antarctic Support Contractor who work directly for the NSF US Antarctic Program, leading and helping us plan the logistics of getting to Hercules Dome and getting back from Hercules Dome with ice. And then of course, the National Science Foundation, which is funding the work. And much of the work after we get the ice back will be done at the National Science Foundation's Ice Core facility near Denver, Colorado. So the goals of this webinar and broader project goals are not just to get some ice and analyze it, but to provide avenues for new participation and new collaborations in polar ice core research. Because of the time we have, drilling is not expected to start until at least January 2024. So there's a few years of planning to do. And the extra lead time that has resulted in part from the pandemic means we really have a fair amount of time to get the word out about this project and bring new people into this field. And when I say this field, I don't mean entirely just ice core measurements per se, but associated science. So I hope that we'll get across some of the ways in which this ice core project can lead to additional science. And we encourage everyone to consider coming to our May workshop, May 10th and 11th. You can go to the Hercules Dome website to find out, to register for that meeting and contribute to it. So here's a brief outline of what I'm going to talk about today. Why are we going to Hercules Dome? What's the glaciological setting there, which is a section of the talk that TJ will lead. A bit about the coring technology we'll use, the logistics and planning, and finally, how to be involved and some time for questions. So why Hercules Dome? I'm going to give just a couple of examples of the sorts of things that motivate ice core projects in general and Hercules Dome in particular. So example one, this is a beautiful graphic produced by Thomas Bauska at Cambridge that shows most of the, I think all of now of the long ice cores that have been drilled in Antarctica over the last few decades, and shows their depth and their approximate age at the bottom. And here's the additional ice core we hope to obtain, that we will obtain at Hercules Dome. The target depth is around 2,000 meters, and the target age is over 150,000 years. So one of the things that that figure illustrates is, a lot of ice cores have been drilled. Why do we need lots of ice cores? Hercules Dome in particular is special because the accumulation rate is relatively high and the temperature is relatively cold, some values shown there. And those are really good conditions for obtaining high resolution and high quality trace gas records. The very well-known record of carbon dioxide is shown at the bottom, going back over 800,000 years. And something that you may not realize if you're not involved in this sort of work is a plot like this is the result of many, many years, decades indeed, of work and multiple ice cores. So that graphic at the bottom, also produced by Thomas, is actually a compilation of data from, as shown here, multiple ice cores. So shown in gray are where data are available for each of these cores and the length of the core in age. Shown in blue are the regions of data from those cores that Thomas used to compile the full record at the bottom. And those choices are a combination of availability of ice, resolution of the measurements made, and quality of the measurements made. Some ice cores at certain depths will not have high quality gas data because of the presence of brittle ice and other issues that can arise, especially in some of the older cores where just time has gone by and breakage has occurred and that sort of thing. So getting a long record of gases cannot be done in a single ice core. It needs to be, multiple ice cores need to be combined to do this. Another thing from a US perspective is that although collaboration is one of the strengths of ice core research, international collaboration, it's also true that if you're a beginning researcher, for example, if you've got a new idea for a new kind of measurement to make, you need access to ice samples. And in the US archive, the limit of available samples is really pretty short in length. It's illustrated by the blue bar on the graph at the bottom. This is essentially the age limit of good condition ice samples for gases in the US archive is limited to the age of the waste divide core, around 68,000 years. If we're successful at Hercules Dome, as I fully expect we will be, this is the additional time period that will be available in the US archive. So we'll go back, our target is to go back through the last interglacial period, at the peak of which is at about 125,000 years ago. So greater access to samples, which are in archive for new or existing researchers to do novel research is one of the goals of this core. Related to this, Hercules Dome is, as I already mentioned, it has a relatively high accumulation rate. And the accumulation rate is a really critical element of the resolution of the ice core, and in particular, the resolution of the gases. The effective resolution that you can obtain on gases is determined essentially by the gas trapping time, known as delta H. And for an ice core like Dome C, where the long 850,000 year CO2 record comes from, delta H is on the scale of thousands of years. And a rough rule of thumb is that the effective resolution of gases is 10% or so of that, maybe a little bit lower. So the resolution is in the century scale. A place like waste divide, shown at the bottom, has a delta H that is century scale, meaning that the effective resolution of gases can be at the decadal scale. But as you can see, that very high resolution record at waste divide is limited to the time scale of the waste divide core, which is only 68,000 years at the bottom. Hercules Dome, here's an estimate of delta H for Hercules Dome that TJ made that shows that because of the conditions there, the cold temperatures and the relatively high accumulation rate, Hercules Dome should be the highest resolution record obtainable that goes back longer than waste divide, back through the last interglacial time period. Okay, so example one is essentially about resolution and complementing other records for gases. Example two is specific to the location of Hercules Dome. Hercules Dome is in East Antarctica, but it's in the Western Hemisphere at the edge of the West Antarctic ice sheet is illustrated here. This map shows all of the deep ice courses that have been drilled and whether or not ice from the last interglacial was obtained at those locations. Note that there's a couple of green circles there. One is Hercules Dome, where we hope to get last interglacial ice. And the other is the SkyTrain ice rise, where the British Antarctic Survey folks recently drilled, and they may have last interglacial ice there as well. We will see. In the event that the West Antarctic ice sheet collapsed during the last interglacial period, which remains an unknown thing, but it's quite likely, both SkyTrain ice rise and Hercules Dome certainly still existed at that time. Lots of other places that we've drilled in West Antarctica, like the Waste Divide ice core, would not have existed at the time. There's no ice left from that time period at Waste Divide because of melting at the bottom, but there may not have been ice at the time anyway. We don't know. Hercules Dome is sitting kind of right at the edge and in a sense would have been waterfront property had the West Antarctic ice sheet collapsed. And as I'm sure most of the folks on this Zoom meeting know, this is one of the really important questions in Antarctic glaciology, indeed in climate and glaciology. How sensitive is the West Antarctic ice sheet to climate forcing? Did it collapse during the last interglacial period? So in addition to, or because of its presence, location next to the West Antarctic ice sheet, there's the potential to obtain information about the timing of collapse if it occurred and how much collapse occurred. So these slides illustrate this in a couple of different ways. On the left are some calculations of the back trajectories of moisture that reach Hercules Dome. So you can sort of think of these as probability density functions for where moisture that reaches Hercules Dome originally evaporates. And at the top left, you see Hercules Dome. At the bottom, you see the same calculation for a number of existing East Antarctic ice cores. And a critical point is that even though Hercules Dome is in East Antarctica, it's very much a West Antarctic location. It's getting moisture from storms that traverse the West Antarctic ice sheet before they reach Hercules Dome. On the right is a similar kind of plot, but this is based not on modern data, but on simulations we've done with a high resolution weather model, both for modern conditions and for the last interglacial period under the assumption that the West Antarctic ice sheet collapsed. And the key point here is, so what's shown is the content of moisture as a map of each location where a moisture bearing storm is reaching Hercules Dome, how much moisture content was in that storm track as it headed towards Hercules Dome. So the modern condition is shown in the top, and it's very similar, of course, to the data shown on the left, which is good because it means our simulations look like the modern climate. When you remove much of the West Antarctic ice sheet, you change the Antarctic topography, and this changes the atmospheric circulation, and the moisture source trajectories to Hercules Dome change. And this has a bunch of implications. It implies that relative to other locations during the last interglacial period, Hercules Dome should have higher snowfall if the West Antarctic ice sheet collapsed. And in our simulations, you also see higher temperatures and changes in the isotopic composition of the snow and changes in the spatial distribution of the snowfall. We believe that we will be able to extract that kind of information from a combination of radar data and the ice core itself, and therefore be able to say something quantitative about the timing and magnitude of West Antarctic ice sheet collapse if it occurred. Okay, and this little video of snowfall is a reminder for me to turn this over to TJ Fudge, who will talk about the glaciological conditions at Hercules Dome and show you why we're convinced we can actually obtain a good ice core at that spot. TJ.
Great. Thanks, Eric. So Hercules Dome has been identified as a good spot to drill a deep ice core, at least as far back as the ITAS traverse. In this paper led by Bob Jacobel and Eric, is kind of put forth as an optimal site for deep ice core drilling. So as part of the ITAS traverse, there were radar produced that imaged beautiful internal layering at ice thicknesses of up to 2,800 meters. And there was also a fern core drilled, which showed good annual layering that can produce a well-dated time scale here shown as a comparison with the volcanic records from the South Pole ice core. The thought from the existing maps were that it was a relatively simple ice dome, but with, Eric, advance, please. But with kind of better satellite altimetry, we can see that Hercules Dome is not the kind of simple dome that was thinking, but instead kind of has a main ridge with kind of 3 different areas that we've kind of named, and we're naming these based on the grid map directions. So, so we have West Dome here, which is kind of the highest summit, and then a ridge of about 70 kilometers extends to the East Dome area, which is near where the ITAS traverse went. And then if you come grid south, down from East Dome, down that topographic ridge, you kind of end up at a flat spot that we're calling South Dome, even though it's not a true dome in its own right. And so I just wanted to go through the terminology so that you have an understanding of the locations that I'll be talking about in the next slides. So the summary of the field work is that in 1819, we were able to get some day trips out to South Pole, which is not the kind of month-long field campaign that we had hoped. But these data proved to be very helpful, as I'll talk about in relation to West Dome. In 1920, we had a much fuller field season with a lot of work from UW graduate students. And then this past field season, there was no field work, as you can expect. It's not looking good for the next field season to have significant measurements, but maybe some repeat surveys can be done. And so then another significant field season planned in 22-23. So Eric, will you advance? So here's kind of a map. This is showing the deep radar layers that have been collected in those first 2 field seasons. I'm only going to show radar images from the 3 megahertz deep sounding radar today. Those are the profiles that are in green here. We also collected shallow radar in most of these locations to infer accumulation rates, and then have done a variety of phase sensitive radar measurements. And I'll focus in on the ones done over at West Dome, because we've been able to repeat these to look at in glacial vertical velocities. Advance, Eric. All right, so starting off at East Dome near where ITAS was, we also imaged the deep ice like ITAS did, but with kind of a fuller picture. We can see that the topography, the subglacial topography is quite complex. Ice thicknesses approaching 3,000 meters, but in very close proximity to where it's only 1,800 meters. And there's beautiful internal stratigraphy, but the thicknesses of those packets seems to vary as you go into the trough. And you'll also notice that the surface topography is a bit complicated, where the surface topography seems to be being affected by the presence of that trough. So the overall takeaway, if you advance, Eric, is that East Dome has complex surface topography, complex bed topography, and has beautiful internal layering, but it is fairly complex. So this is not a site to recover an easily interpretable ice core. Moving down to South Dome, so going grid south down that ridge, we can see that South Dome is an overall shallower site, still with bedrock variations, but of smaller magnitude. And the layering is, once again, beautiful, coming right kind of up to the bedrock at the bottom. There's some hints of upwarped layers underneath the divide at about 15 kilometers on this, but we don't have repeat measurements to look at the glacial vertical velocities yet. So advance, Eric. So kind of the main takeaways from South Dome are there's slow flow down ridge. We don't have the vertical velocities yet, but there is very good layering to near the bed at depths of 18 to 2,100 meters. All right, so on to West Dome, where we have a little bit more information. In the radargram, you can see a black line through the center, and that's just because the way the whole transect was done, there's a little bit of a gap in the center, so just a little bit of missing data. But you can see the surface topography is simple, what we would expect of the dome. The layering, once again, just like at South Dome, is going right up to the bed. And so what we're going to look at now is what the end glacial vertical velocities tell us. And so you can see that there's two very different profiles of deformation between the site that's 5 kilometers from the divide, and then which is blue, and then the red site, which is 1 kilometer from the divide, kind of within the divide region. Eric, will you advance one? And so the difference here is kind of divide flow versus flank flow. So this is kind of when you get to low deviatoric stresses, you produce a different deformation pattern. It's what gives rise to Raymond arches that you might be familiar with at sites more typically along the coast. And I'll come back to why I'm showing the profile from 4 kilometers instead of 5 kilometers, but the two are actually very, very similar. So maybe the most important point from the divide flow existing is that it's a good indicator of a frozen bed. It also kind of tells us that the glaciological understanding, the setting is simple and we understand it. And then it also helps us figure out what the depth age scale and the deeper ice is going to be, because it says we have deformation that's typical of a frozen bed with that has these lower deformation rates deep in the ice column. Will you advance, Sarah? So now what I'm going to look at is just using the accumulation pattern that crosses this divide, just looking at the top internal deep layer. Will you advance? And so if we try to model this deep layer with the existing accumulation rate, but with just flank flow, we produce a layer that doesn't fit very well in the center divide region. When we include a parameterization of divide flow, we get a much better match. And in this case, it's kind of divide flow for the last 1,000 years. Advance, Eric. And so we have an idea that divide position has been stable for the last 1,000 years. We have ongoing work to infer the divide position for older ages. And there's hints of a Raymond arch that you can see kind of at kilometer 4 in the radargram, where the peak of the upwarp layers is over an area with bedrock that's a bit deeper than the peak, which is at about 5 kilometers where the black band is. But it's difficult to infer this in regions of varying bedrock, so that work is ongoing. Advance. So the takeaways from West Dome are it's a defined dome, it's likely frozen given the divide flow, and that there's layering to very close to the bed at depths of 16 to 1,800 meters. Advance. And so the expected depth age relationships, all I really want to emphasize here is that the last interglacial at 120 to 130,000 years ago is expected to be about 100 meters off the bed in a 1,600 meter depth scenario, and closer to 200 meters off the bed in a 2,100 meter depth scenario. Advance. And so kind of the potential for ice coring sites at Herc Dome are that West Dome is likely to achieve the ice core goals, South Dome has promise but needs more investigation, and East Dome is unlikely to achieve those goals. And so with that, I'll kick it back to Eric.
Thanks very much, TJ. Before I move on, I just want to comment that the vertical velocity plots that TJ showed that result from the field work done over the last couple of years, including a very long, difficult field season by UW graduate students led by Kenya Christensen. These are beautiful data. This is fairly new technology, and this is the first ice core project that I've been involved with where we actually have information like that before we go and drill. So that's really, really promising. You might be wondering, why haven't we decided we're going to drill it at West Dome already, because it looks so beautiful? And the answer is, it's a really great site, but we want to know more about it, and we want to know more about South Dome before we make a decision. One advantage that South Dome might have is that because it's deeper, we're going to have more opportunity to do borehole thermometry than we would at West Dome. Anyway, moving on to just some logistics things. One of the reasons I want to show this is simply that some of you may be interested, but also for those new to the ice coring world, this gives you a sense, hopefully, of kind of the scope of this sort of project and why we have time for planning and involvement, which again, I think is a real advantage. It's a little bit like we're launching a probe to Mars. It's not going to get there for a few years. So there's time now to start thinking about collaborative work. Of course, with Mars, you need to decide much earlier because you've got to put all your instruments on the spacecraft. So for drilling technology, we're going to use the new 403,000 drill, which is being developed by the ice drilling program folks at the University of Wisconsin. This will produce 9.8 centimeter wide by 3 meter long ice core sections. And this is essentially the same as the drill that we used at South Pole, where we successfully drilled to 1,751 meters in just 2 seasons. Very successful project, great core quality. Everything went extremely well in the field. And the drill design borrows very heavily from older Danish designs, the Hans Tausen drill that you may have heard about. One of the great things actually about this, the ice drilling world, is the amount of collaboration between different groups. And in particular, in our case, the Danish group and the US group, technology has gone back and forth. We spent a fair amount of time debating whether to use the South Pole drill or possibly to use the old disc drill that was used at Waste Divide. But it turns out that the disc drill, it was a fantastic drill that reached 3,300 meters at Waste Divide and produced 5.25 inch wide diameter ice core. But we will save at least 50% in logistics, transportation, fuel, and a fair amount of time as well by using this smaller drill. Another comment about the technology, which is important, is that we're aiming to get last interglacial ice and beyond, and there will probably be a lot of people that are interested in having samples of that ice. So we expect that we'll also be doing replicate coring to obtain extra ice from specific depths. The last interglacial would be one of them. There may be others that people are interested in doing. Replica coring is not something that's funded to be developed, but it is something that people are interested in, and there are plans sort of beginning to be discussed. This is something that researchers who think they have good reasons to do this should be getting involved with, talking to us, going to meetings of the Ice Core Working Group and the Subglacial Access Working Group, et cetera, and making their voices heard about the importance of this, because if good science can be done this way, it's very likely to get supported. Similarly, borehole logging after the core is obtained, and potentially subglacial drilling should also be possible. But now's the time to start talking with each other and with us about how to make that happen. Again, advanced planning is important. And one of the purposes of this webinar and our May meeting is to start talking about those things. So if you're interested, please come. Okay, drilling, I just talked about. Other logistics aspects which may be of interest. This is part of the reason for the amount of time it will take to actually be in the field doing this. We have to get a lot of equipment to Hercules Dome. 250,000 pounds is just the drilling and drilling fluid in camp. There will probably be more. We're lucky, however, that there's a very well-established traverse route, which is used a couple times every year to take equipment and fuel from McMurdo Station across the Ross Ice Shelf up through the Transantarctic Mountains to South Pole. And to get to Hercules Dome, we just have to take a left turn somewhere up on the polar plateau, as illustrated there. And of course, this has been driven already because the ITAS traverse back in the early 2000s that first went to Hercules Dome crossed through the Transantarctic Mountains from West Antarctica to South Pole. So we know that this can be done, and it's just a matter of getting the plans together and making sure that all the equipment is available. There could potentially be science to be done along with that traverse. Probably not a lot, because they don't want extra people or anything like that. That's just something else to keep in mind if that's of interest. I didn't mean to leave the sound on, but it's sort of fun. We're going to drive to Hercules Dome to get equipment there. People will then fly in, probably via South Pole, possibly via South Pole, for acclimatization to the altitude. And then, of course, the ice cores will be returned by airplane, by Hercules aircraft, and brought back to McMurdo and then shipped to the US. Just a couple more things to talk about before we're done here, but in some ways, this is the most important part, the planning schedule. So as I've said a few times, the timeline means that drilling is not going to happen for a few years. It is certainly not going to happen before January 2024. That's the earliest that NSF thinks we can do this. That means that drilling will be complete somewhere in the 2026, 2027 timeframe, maybe a year later. So some key timelines are illustrated in blue. First of all, the first annual workshop in May, please come. The timing means that proposals, now's a good time to start thinking about proposals to do work on the core or related work, or work that's inspired by the Hercules Dome, by the fact that the Hercules Dome project is happening. Now's the time to start thinking about and talking with colleagues and recruiting students and things for ideas related to preparatory work. For example, if you need to build new instruments to improve your analytical capability in the lab. It's definitely premature to be writing proposals for analysis of the ice core, since it has not been obtained. But somewhere around 2023 is probably about the time when the first proposals for analysis of the core would be considered. Note that these are not official NSF statements. I'm just giving you a general sense of what is probably feasible. And finally, June 2025 is the first likely sampling season at the NSF ice core facility. And then, of course, things like borehole logging, replicate coring are beyond 2025. So this project is still going to be ongoing in 2026 to 2030, maybe beyond, depending on interest in things like borehole logging. And this means there really is an opportunity to include people. Consider that students who are beginning undergraduates now could be graduate students by the time the project is underway. Current graduate students, even current beginning graduate students, could potentially be principal investigators submitting proposals and leading aspects of the project in the future. There's time to develop these relationships and bring people into the polar ice core world and polar science in general. There's also time to develop broader communication strategies, films, artwork, science outreach, etc. So the bottom line is collaboration on this project and on adjacent work is encouraged and sought. Again, come to our workshop, get the word out, etc. And last point, the workshop will have some time for talks, not a lot of long talks, but time for plenty of short talks to introduce your science or introduce your ideas and network with one another. We have a number of invited speakers who are committed to coming to talk. And I want to emphasize that although this is sort of primarily an ice core project that's motivating this, there's a lot of related science, and some of our invited speakers are not ice core people. They're ice dynamicists, such as Natalia Gomez. Ted Scambos will come to talk about the Thwaites project, which is quite different, but scientifically highly related because the emphasis on possible Western ice sheet collapse. Lawrence Young and Sarah Shackleton are both chemists who work on proxies relating to the atmosphere and the ocean, respectively. And finally, Guillaume Mauget is an expert on policy and communication about sea level rise, which is obviously relevant to Antarctic science. So I think it's going to be a really interesting meeting, and I hope you will come. registration is open, so please take a look at that. And I think our registration deadline, if you want to give a talk, is April 23rd. Finally, also join us for Eric Wolf's talk on April 15th. Eric Wolf is an ice core expert and leader at the University of Cambridge, and he'll be giving an overview of Antarctic ice core science with some emphasis on his own projects at the SkyTrain ice rise and the relevance to Hercules Dome. So that concludes the sort of formal presentation. Questions and discussion, please ask in the chat window, and we'll do our best to